Okay, welcome everybody to an introduction to type classes. It is the path of enlightenment. We start with the idea of higher order functions, just a short remembrance so everybody knows what I'm talking about. Then the concept of separating data and functions, where in object-oriented programming you usually combine data and functions into one object, but for type classes we have to separate them. But then, after we separated them, we want to bring them back together. And type classes are the way to go. But type classes are not only data and functions, they are also laws, which I'll explain when I get there. So I assume everybody's seen how to use higher order functions in this case with array map. Who's seen it? Hands up. Used map in any language, in any kind? Yeah, okay. Expected as much. So there isn't too much to say about them. So over the course of the different steps, I'll always talk about some common structures. In this case, one of them will be the interface mappable, which is an interface which defines that you can map. So imagine a list you can map over, so you could implement the trait mappable with that. You could also implement mappable over other things, for example, a map. But the basic gist is this is something you have a map operation on. Now, the next one, this one looks a little bit more interesting because of the type signature. You don't fully have to comprehend it to follow along. It's just trying to say that the argument you pass in has to be of exactly the same type as the thing that is implementing the Ependymal interface, or trait in this case. I don't know how many of you have tried as a fun project implementing a type-safe equality that actually checks that the other type is the same. Okay, one or two. Now, this is extremely hard, at least with the JVM type system, where I have the most experience with, besides Haskell, it's basically impossible. There's always ways how you can escape saying that this other thing that I get passed has to be exactly the same thing as itself. If you want to know more in the Scala type system, you can Google Typeclass current type. He has a very good explanation on why that is the case, but I don't want to go all the way into that. The other thing is nowadays we have JSON everywhere, so we got to transform our data structures into JSON. In this case, it's a very simple interface, which just says, transform me this object into a JSON representation. Now, for our first step, we will separate the data from the actual function that implements that operation. So we have a data type, this is Elm. We have a data type which represents a person, where you have two fields, a name and an age parameter, and then you have an entirely separate function which encodes that into a JSON object. So we now separated the data from functions which operate on that data. Now, I've talked about this concept with some people from the object-oriented world, and the first question was, where do you put the functions when they don't live inside an object anymore? Like the idea on grouping functions. And usually you just don't care, because the functions work anywhere, data types are introspective, so you don't have any public-private distinction, so you just implement your function anywhere. And specifically in Haskell, or also now for Elm, there's a fancy search which lets you search by type. So you can say, I have this object and I want to convert it into JSON. Then you put that in as a type description into the search engine and it pops you back the function you're looking for. So you kind of lose the idea of introspection, but you gain the separation and the distinction between function and data, that they're not intermingled anymore. Now, with the Mapable interface, you can't implement that in Elm. simply because there are no higher kind of types. It's a specific requirement, so the f is not representable in Elm. However, you can just do list.map. You just have to specifically say which container you want to map over, and therefore you still have the map operation just fine. But you cannot implement a mappable interface. That's not possible. This one's Elm Code. Yeah, that's the Elm symbol. So specifically, I have different languages, and it's just Elm has the very distinct idea or distinct feature of separating data and functions, which you find in a lot of languages. It's just it's best language to demonstrate the idea of the separation. That's why this one here. And the next idea is the Ependymal Interface, which actually works just fine. You just make a data structure where you have your append operation in there, and then you can create it and use it. So this will just append to 2 strings. The ++ operation here is you can append strings and lists with it. This is a little bit of magic because it uses some compiler magic to actually make the ++ work for strings and lists. Okay, so we separated data and functions. And now, to get to type classes, we will have to bring them back together. Now, with the Json encoding, this is an example for Rust, which also has separate data and function implementations. The struct is the exact same thing as before. The I32 just stands for a 32-bit integer. And you can now implement to JSON for something. And this is also entirely separate from the actual object itself. Although you have to put it in one of the 2 files, because otherwise you could have 2 implementations in different files, and the compiler would not know which one to pick. So you will have to put this one into the same file as person. Otherwise the compiler will complain about it. I did not actually implement the function here because it does not specifically explain the concept. It does not bring any additional value to the explanation. The basic idea here is that you have an implementation to JSON for person. While it could look like this is part of the class, it's actually, the important distinction is that it's getting looked up by the type, not by the class itself. So while this one takes self as a parameter, which means that it's kind of like Python, where you take the first value is the object itself. It's actually separate. You do not have to take self as the first parameter. You could also have an entirely distinct operation, which is not does not take the self as value.
So what's the type in this case?
The type is so the return value is value. The type is the input for to JSON for person. Did that answer your question?
Yeah.
So for Mapable, the trait Mapable also has a bit more interesting type signature because of how Rust works underneath. And you can also write a Mapable implementation for a linked list. Although this is not entirely idiomatic Rust, it would work differently if you'd actually use it. But this is to demonstrate the point that the idea again that you have an implementation that is separate from the data structure, and it is being joined together by the type. So if you want to call Mapable on something, the compiler goes looking for, or sees you have a linked list, you want to map on that, and it goes looking for the implementation of Mapable for linked list, which is the idea behind Mapable here. Now with Ependymal, it works exactly the same, except here you don't have the problem anymore that you cannot say the other type has to be exactly the same as itself, because you can simply say, well, it has to have the same type as the actual implementer, because you now have a reference to that, and you don't have subtyping, which messes the whole thing up. you can now specifically say that the thing itself and the other which you want to append have to be exactly of the same type. You cannot do any interesting shenanigans with subtyping anymore as you could with Scala. So we have a mappable, and now we want to make a functor out of it. The distinction between mappable and functor is that a functor has laws associated with it. So let's say you see an arbitrary map function somewhere in a library. What would you expect from it? Like, this is basically a general rule on you pass something a map function, or you pass a function to a map. What would you expect of the outgoing data structure? It has the same length, yes. Could you repeat that? Sorry, I could not hear that acoustically.
So the function f is applied to every element in the input.
Yeah, so it's applied to every element. Other ideas? For example, what would you expect from if you chain two maps? If you say map F, map G. Yeah, so the idea of the composition, which means that you actually have map F, map G, is the same thing as if you just map once and you apply F first and then you map G. What you the point mentioned with has the same length is actually not entirely covered by those here. It's usually the case because it's not possible. I haven't yet seen a data structure that does not obey this if it implements the functor laws. It's a rather specific case. I have a good example though for that. So let's talk about Java 8 optional. Who's worked with that? Okay, a few. So Java 8 optional has a very distinct design decision. It is here to combat the idea of null. So an optional is something that you use if you don't want to deal with null values in Java, which led to the design decision that an optional may never contain a null. However, they added a method called map, which has some interesting properties. Because of the law that it may not contain null, it actually matches up the composition. So you have two functions where the first one always returns a null, and the second one checks if it's actually a null, because a null is always a value, even if it's inside an optional. Or if it's valid to check if the thing inside of a null is optional is null. So if you compose those two, you actually get different results. So the composition does not hold for the Java 8 optional. If you go run around, you find a lot of people ranting about that. I think Atlantacion had a rather long blog post about why that's a bad idea. So this is something that comes from the ivory tower of functional programming that introduces a behavior that you usually would not expect entirely. So you know specifically you have to know that the optional behaves differently for nulls and not nulls. And you have to specifically pay attention that you do it correctly. So it behaves differently than other maps. So I was coming back to the idea of set and the idea that everything has to be of the same length. So I did some experiments with it, and it actually kind of works, but only if the hash code and the equality, which in case of JVM or ORT in case of Haskell. I'm not sure how JavaScript sets work exactly, or well, the object keys in this case. And they have to include everything. So for example, if you have a data structure inside of the set that does not include everything, does not use all the fields to compute the hash code and the actual identity in the set, you can actually create some weird data structures that you can map over them, and you can lose some. However, this is, so it's kind of, it still obeys, most of the case obeys the functor law, but it's still not considered a valid functor. Mostly because the functor says that you can transform it into anything. However, with a set, you have to have some operation figuring out what is its set identity, like what is its hash, what is its hash code. So you can't make a lawful functor for it because you have a condition on what the output is. So the next one is our good old append. What would you expect from two things that you can actually append together?
This?
Yes, that is the same type, should be guaranteed by the type system. The laws are more about values. So in this case, it would say that if you say if you add A plus B and then C together, you should have the same thing as if you add B plus C together and put A in front. As usual, there's a good old example to explain where this does actually not hold, which is floating points. Where floating points arithmetics are, yeah, well, this is actually already bad code because you cannot reasonably compare floating point numbers. Now, this actually leads to some interesting behaviors. I've actually saw some people in the Go channel of the company. They had a program which summed up some things and had in the end a map from string to a floating point. And then they added up all the values, which worked just fine. However, they got a different result each run. It was just slightly distinct, but it was a different one each time. That was because Go actually has the point where they do not want people to rely on the order in a map, so they randomize it each time when you iterate over it. So you get different results. So for Json encoding, there aren't really any laws in and by itself. You can theoretically, usually you check for round trip laws, which means you have something that encodes into JSON and then decodes back, and you simply check if it round trips, which kind of works. This has, however, sparked a discussion in the Haskell community that JSON encoding should actually not be implemented via Typeclass because there's no real laws for it. Only the things that have laws associated should actually be Typeclasses. From the various Typeclasses that implement lawless functionality, that idea has never gained too much traction. So now we're here with JSON encodings as Typeclasses. Now, how does a typeclass look like? So this implements a operator. Some call it a TIE fighter operator. Spaceship one is, I think, the one with the equal sign in the middle, with the associativity. And this is called a semigroup. This is basically appendable with the law of associativity, that then it's a semigroup. If you don't have the law, it's just an appendable. With the functor, it's exactly the same thing. I cheated a little bit. In Haskell, the functor is actually called fmap because that whole typeclass business came way later. And they already had map taken for just mapping over lists. So they called it fmap for functor map. But usually it's called map everywhere else, so I just left it as map here. And the idea here is the two laws is the identity law, that when you map over the identity function, you get the exact same thing back. And the other one is the composition law. Dot is the composition operator, which says compose those two functions and then apply them over the data structure X. Now, we've seen a few type classes. So usually what helps the best with learning new concepts is building an intuition for them. So there's actually 3 kinds of how you could describe type classes and to gain an intuition for them. You could just look at them as a class of types and in more or less an is-a relationship. You could say this one is something you can append together. And the formal way is saying this type has a semigroup instance. So you could say that list is a member of the semigroup class. And the expression of that is that it has a semigroup instance. And you can call the append function from it. The second part is it's basically a dictionary from a type to a function. This usually comes best if you, in Python, objects are basically dictionaries from names to functions. It just happens to be that the syntax looks a little bit differently, but if you do a little bit of reflection work in Python, an object is a dictionary, as most other things in Python, and your mapping from something to a function is you have a string. So you could say Python is stringly typed. And with type classes, you use the type to look up things. And then that way you have a dictionary from type to function. And the third idea is a type class is an actual constraint. It constrains which kind of values or which kind of types you can actually input into that constraint so that it's valid. For example, you can append, if you say, I take a type which you can append together, that means I can put in a string there, or I can put in a list there. I could not put in for example, an email address, because appending email addresses does not make a whole lot of sense, because if you append 2 email addresses, then afterwards they're not an email address anymore. Now, since we have a semigroup with an append function, we can make more out of it. So for every append function, or let's call it plus operation, an addition operation, you always also have a 0 element. So for integer addition, you have 0. For integer multiplication, 1 is the null element. For string append, the empty string. For list append, the empty list. So you have this is basically the next step of a monoid, where you have a 0 element, which allows you to compose, or which allows you to use or to define a 0 element for something. So the syntax here basically means that each monoid has to also have a semigroup instance. So a monoid does not make sense, a 0 element does not make sense if you do not have a addition operation. So there's a few, I already mentioned a few monoids. There's also a few more, for example, the idea of configuration. A lot of people map them to monoids, which basically means that you have some configuration, you have a default configuration, and then you can append changes to that configuration. Basically, you have another configuration with some changed values, and you append it, and you get a configuration with those 2 values merged, depending on how you define the merge operation. Usually it's override. So here we also have laws, which are purely the identity laws. So if you append the identity, you get back an identity on either side. They're mostly called right and left identity, depending on where you put the actual identity itself. Now, a little story from my side is I started out programming Ruby like 9 years ago. I did natural language processing, which is a fancy word for operating on a whole lot of documents. like a very primitive operation which actually gets you pretty far is just count the number of words in a document on how often they occur, which you usually do with a map from string to usual integer. And then you just have a rather big map from, let's say, the word "der" occurs extremely often in an English text, which is usually on the top. And then you have a few longer words which occur only once or twice. Now, the question is, if you have two maps, how do you merge them? Usually, or the way I did it back then, is you write a reduce, which appends each single element to the new one and makes sure that they get correctly mapped, or they get correctly appended. Because if you just use the default functionality, what usually happens is that you actually lose one of the keys, because the default for a map operation is just drop either the left or the right side, depending on which operation you use, which is not what we want here. Instead, we actually want to sum them up, which is what a monoid is perfect for. Now, back then, I basically had the idea, even if I had a dynamically typed language, if I had a compiler, it should be able to figure out what I was doing, because the types are there, the information is there. Such an idea has to exist, and somebody pointed out, yep, exists, go learn some Haskell. Now I'm talking about Haskell. Sadly, that's not the default for the Haskell map monoid. It actually discards one of the two sides. I don't remember which one. And let's put it that way. Most of the people say it's a bad idea. Some actually like this implementation. In Scala, it's actually the right one, which merges sub-values. Now, this is basically the basics I wanted to talk about. And so far, I mostly wanted to ask if there are any questions so far. So I'm not entirely sure now if I lost everybody or it was entirely clear all the way through. I'll take my favorable answer, which is it was entirely clear. So I mentioned the laws. So there is actually the idea of having automated law checking. So you generate random values, you put them into the semigroup, you see what comes out, if it actually matches to the laws you defined beforehand. Which is pretty convenient, because you can just say it's basically a one-liner for testing, does your stuff actually work how it's supposed to? They actually found some in a HTTP library for Scala. They found some rather obscure bugs with that, where they had some decoding issues with some very specific Unicode characters, which only occurred somewhere on the fringes of the actual Unicode specification. So you can actually find bugs with that. Most of the time, it's just something you write your monoid, you put down the quick check laws, and you call it a day, and you don't have to write any more tests, which makes the actually implementing your own lawful instances extremely trivial. And another thing, I also mentioned a little bit, like this is entirely unrelated. Like, this is basically the material I wanted to cover. I considered just going further down the typeclass route, but the main issue with that is it actually, once you know what typeclasses are, then you actually have the different typeclasses and have to learn them. And each of the Haskell books actually, or the Haskell book for each of the typeclasses has a full-on chapter. And while I assume that most of the people already know the idea of a functor and you also appended stuff together, the actual further stuff I figured might be a little bit short on time. So I figured I'd instead talk about something slightly unrelated, which is, why does the Haskell syntax actually look like it does? Or what are the benefits of it? Now, in JavaScript, or most other languages that look like this, Scala, Java, Go, you pick one, you have statements. and you have expressions. An expression, to nail down the actual vocabulary, is something that returns a value. For example, 1 plus 2 is an expression because it returns a value 3. And then there are statements, which either, usually they just return nothing, null, or actually are an invalid statement, or the compiler just complains about it if you put them somewhere where they would expect a value. In most of the dynamic languages, it just returns their equivalent of a null. In Ruby, it's null. In Python, it's none. In JavaScript, it's undefined. So if you assign the value of the statement val f to foo, it should have been a var, damn it. Then you just have an undefined. Now, the basic question, what's the difference between a statement and an expression? A statement makes a change in your environment. It basically modifies state. Or in this, like the window.alert, it has a side effect. However, in Haskell, it's not possible to have side effects unless you really try. So having statements makes no sense because statements are inherently associated with side effects. There is one statement which kind of has no side effects, which is the variable assignment, which you can convert into an expression by having a let block, which allows you to assign variables in that specific scope. So another thing is, specifically in Haskell, what's the distinction between a function and a value? There is actually none, because there's first-order functions, and actually most languages implement such a thing. There is no specific distinction between functions and values. So why treat them differently in any manner? And also a very basic question, which actually has a profound meaning in non-pure languages, is where do you actually do the function application? Because that is where the side effects happen. In Haskell, that does not matter, because again, there are no side effects. So having a statement anywhere does not matter, or it's actually irrelevant, because a statement cannot do anything. You actually have to pass along those values which do something and put them into the good old monadic context to actually do anything at all. Because if you just have a random thing flying around somewhere, it cannot do anything. So hence you can only have expressions and no statements. And if you actually remove that, you get a purely expression-based language, which is a Lisp. Except Haskell doesn't have a whole lot of, you can write Haskell with a whole lot of parents, but you don't have to. But the syntax in the end is exactly the same as a Lisp, except without all the parents. Yeah. Then, any more questions so far?
I have two questions, but I don't know if you're going to like them, so you can skip them if you don't. And I came a little late, so I don't even know if you covered this. In Haskell, we sometimes refer to type classes as being ad hoc polymorphism, as distinguished from parametric polymorphism. I've never discovered a good way of explaining the difference. Do you have one? That's the first question. The second question is, I don't know if you're aware, but some people think type classes are a bad idea, and there are other ways of implementing the same kind of functionality without using them. If you know about that, maybe you can explain why that is. If not, you can forget it.
So I know what is exactly parametric polymorphism. I'm not entirely sure about that definition.
Like generics, I guess. Like if you have some function from like A to B, it's polymorphic to type A, versus a type class where you're defining some constraints on the type variable. Any polymorphic function is parametrically polymorphic.
Also, is that not like inheriting classes objects?
I haven't thought in OO terms in so long that I don't function that's like from some type variable to some other type variable, or even from a type variable like a to int, for example, is parametrically polymorphic in the a. You can have some type class constraint on the a, and then you have ad hoc polymorphism, which is a different kind of polymorphism. So anyway, maybe never mind. It's just it's not clear to me like how to explain what the difference is or why it's even significant. It's just if you had some idea about it, it would have been interesting. But I think it's probably beyond the scope of what you're talking about.
So one specific thing kind of related to that is how they actually came up with the idea of type classes in the first place. They had the problem of adding numbers together. How do we implement the idea that you can use the same operator to add integers and doubles together? So with that, they first had basically compiler magic, where the compiler just picks out the correct operation for you. But then they figured we don't like magic too much, so we'll provide a first-class idea on how to do that, and that's how ad hoc polymorphism was born, or the idea of type classes. So they implemented a number hierarchy with that, and then other people came up with it and figured, oh, we can do other stuff with this. So it was actually considered one of the most experimental features of Haskell ever, which was usually a very conservative language. And yeah, it's basically become its entirely defining feature. And the second question was, I already forgot about it.
There's some debate about whether or not type classes are a good thing. I don't know a lot about it. I'm just curious if you do. Some people say that they're bad and you can accomplish what they accomplish in some other way.
Absolutely. Like Elm is the prime example for that, where you can accomplish a whole lot without type classes. It's mostly it's like any other abstractions. It's just the idea you have to learn the abstraction versus you actually have to, you save code because you can use abstractions versus an extremely clarity of code where you don't use any just function composition, and you can get extremely far with that. However, there's always a limit of how much you can actually express. And the other way versus objects is that type classes are strictly more powerful than interfaces, simply because you cannot implement a monoid with an interface. You basically have a chicken egg problem where basically, if you want an empty, you have to have an object of that first because that's where the method is being declared. But you don't have that yet because you actually want an empty element and you have a chicken egg problem. So that is strictly more powerful in that regard. Let me think again about the... Also, if you want to compare the whole type class idea to objects, is that if you have object level dispatch, for example, in a JVM, you have the idea of overloading, but let's say you can only have one name. Then you just have overloading on the first parameter, which is the object itself. So you basically also have some kind of, actually, no, that doesn't work out because you still have to look it up on the value and not based on the type. So you can actually have in the JVM at least, you can have either method implementations on the class or on the object itself, which means if you have it on the object itself, it's not actually anything related to a type class anymore because you're looking up functions on the value itself. Yes, any more questions?
You mentioned that you could verify the laws by using something like quick check.
Yes.
Are there languages where the laws are like part of the definition of a type class?
I'm not entirely sure if Idris has the ability to actually implement the laws on the class itself. I can absolutely imagine that Coq has something like that because they're all about law checking. So I would assume that Coq certainly has it. Idris probably, but I'm not 100% sure. And in Haskell, which is more pragmatic and just do it manually, which is not. I mean, you always have a degree on how much you actually want to check. And usually having the instances is, I mean, the automatic law checks is pretty decent.
So I heard that earlier today or yesterday that Scala checks for laws
Ah, cool idea. So how is that specifically via doccheck or something like that, or?
I thought it was Scala check. I don't know what part of it. And of course, the comment has to have a certain structure.
And then you have mostly you can just say this is a type class instance of this. Yeah, I can see that working.
That's the last syntax that it makes.
Beautiful.
But everything that calls it makes it.
Yeah, doccheck expanded. Right, I also have one last thing, which is basically how do you break stuff with how do you break the functor laws of set? Now, this is a little bit of a contrived example because it basically defines an hash code and an equals, which is basically how a set in Scala does the equality check between two objects. So you basically define that you only check the integer and not actually the string, which means if you only modify this, if you only modify the string, that means it does not actually check. It does not change the identity inside of the set. So that can lead to some interesting ideas. So the idea here is that you set the thing that actually matters for the identity to one value, which means it gets reduced to one element because of the set checks the equivalence between two objects. So they see, oh, it's the same, even though they're different. And then you only end up with one value. And the second operation takes the value which we ignored and puts it into the value which you actually care about, which then means if you actually go out of your way, you can break the composition when you use map over sets. Usually it's a bit of a contrived example, and as mentioned, because it doesn't have a functor instance in the first way anyway, because you cannot produce an arbitrary output. But it's more like the idea how you actually break functor laws. You can also find those, usually, no, I have nothing to say anymore. Yeah, I think that was also.